Okay, welcome to 716184, and today I'm going to be talking about the Gaussian distribution and the binomial distribution, and I'm going to try and link that to concepts which you might be familiar with, or you should be familiar with from last year, but I'm just going to give you a little bit of reminding. So I'm just going to write my learning objectives here for today. Learning objectives. We're going to remind, or revision, I guess, revise the binomial distribution and the Gaussian distribution. We're going to revise hypothesis testing, type 1 and type 2 errors, and 2 errors. And I'm also going to revise definition of p-values.
You say Gaussian? Is that what the word is?
Yeah.
Okay.
Gaussian. This is named for,
Some guy.
I think there's 2 S's in it, Gauss. When I'm talking, I'll spend about half of my time talking about the mathematics of the situation I'm dealing with, and about half the time illustrating, using numerical methods, what's happening on the screen. I want you to be aware that I'm going to make a transcript of this available, so I don't want you to be scribbling down our notation. I want you to be concentrating on the mathematical resources of the mathematical content of what I'm talking about. Okay, so let's start with the binomial distribution. If I move this over here, actually, can I write on here? I can write on the wall here. Can I write? Can you see on this one here? Is this visible here?
Yep. Follow you around a little bit.
Okay. Binomial distribution. Okay, binomial distribution. The first concept you need is the concept of a Bernoulli trial. This is a two-way experiment with two possible outcomes. So typically, success or fail. That's the canonical one because it either works or it doesn't, whatever it is that you're doing. However, you can think of a coin toss and it could be head or tail. It could be win or lose. Good example. You've got to be a little bit careful with win and lose in a sports situation. For tennis it works because you've always got a winner because you get that tie break and you never have a draw. But in soccer you might have a 2-2 draw, or chess you might have a draw. But a lot of sports you have win and lose. If there is the possibility of a draw, then you don't have this Bernoulli trial structure. It could be male or female.
Date or no date?
Date or no date. And I'm sure you can think of lots of other examples. For the purposes of this course, well, for the purposes of statistics in general, you can turn any measurement to a Bernoulli trial. I'm getting a bit hamstrung for space here. Let me get rid of this lot here. If you have a measurement x, which is a measurement, could be a length, might be a length or a weight, or a time, or a weight, then you can ask, do it again, ask, is x greater than some value x naught? And that, of course, is a yes, no value. So you just choose some value there. You might be looking at the height of people, and you might ask, is this person taller than 5'5", or what would that be, 1.60 m? So it's possible to turn any measurement into a Bernoulli trial. And when I'm doing research, and when I'm not research specifically, but when I'm doing consultancy, when I'm using statistics to make the world a better place, I'd say about half of my time and effort is spent converting measurements into Bernoulli trials and then analysing the Bernoulli outcome. So this is a very, very general way. It looks like a very specific, very, very special type of measurement, but it's not, because you can turn any measurement at all into a Bernoulli trial. And before I forget,
it's a black and white thing.
I'm sorry? It's got to be a black and white thing. If you've got shades of grey in there, we're not talking Bernoulli trial. There are other methods to deal with it. It's got to be black. That's a good example. Black or white. Black or white, if you're looking at chessboard or something. However, normally I use the standard language of success and fail. Actually, the most, I guess, you can have live or die. Quite often I'm dealing with things like very powerful anti-cancer drugs, and your patient will quite literally live or die. So, but I just want to make the point that when we talk about success and failure, of course, sometimes, well, you think of the patient living as being the success.
Living longer.
Living longer, perhaps. Everybody dies eventually, I guess. So you normally think of living as the success, but these are just words. There's no value judgment associated with them. Just because it's a success doesn't mean it's desirable in any sense. It's just a word. I could use it. I could say bling and blong, but you just normally talk about success and fail. So, for example, when you toss a coin, you normally talk about the head being the success and the tail being the failure, but there's nothing better about the heads than the tails. It's just words. Okay, so we can turn any measurement into a Bernoulli trial. So if you have n repeated trials, where n is greater than or equal to 1, n is known. Quite often, we are interested in the total number of successes. Quite often I'll write a little sort of hash symbol for number of successes. Okay, and we'll write R.
Quality of what? Quality of...
Quite often. Quite often.
Sorry.
Quite often. So I'll return to this point in later in the course, but the crucial thing is that because we're interested in the number of successes, I don't really care where they come. I don't care whether all the successes are right at the beginning or right at the end. I'm just interested in the total number of them. So, for example, if I'm interested in gender balances of my courses, I'll say, well, how many male and how many female students have I got? But I don't care if I have the boys first and then the girls, or the girls first and then the boys. I don't care what order they come in. As far as I'm concerned, boy, boy, girl, boy is the same as girl, boy, boy. I don't care where that G comes in my counting. In this case, it's because I've got no particular way of order. I've not ordered you from tallest to shortest or anything like that. I'm just counting you as you come. So the order can't mean anything in this case because I've not put you in any particular order. Okay, so how do we use this thinking? Where's my... oh, there it is. Okay, so if I have n equals 5 trials, that's 5 repeated trials where we have a dichotomous variable. We have a Bernoulli trial, okay? And these trials are independent. Is that how you spell independent? Independent of one another. And I'm going to use rather imprecise language. I'm going to sharpen this up later on in the course. But these trials are independent of each other. So, for example, if I'm looking at the genders of the people here, then it could be the case that this might be a female-only course or a male-only course. And so once you've established that there's a few male students, then all the rest are going to be male. And so they're sort of interacting with each other. The genders are interacting with each other. Or, for example, if it's win and lose, if I'm looking at a sports situation, if I look at a sequence of sports results, sometimes you get on a roll. Sometimes if one person starts winning, they carry on winning simply because they feel really confident. So once you've seen a few wins...
Winning streak.
A winning streak, indeed. So that would break this assumption of, oops, this assumption of independence. Does that come back up?
Yeah, I'll probably just do a second.
That's coming up, is it?
Unlock it at the bottom there.
Oh. Unlock. Right, that's worked. Okay. So when I say n equals 5 trials, it could be any sequence of 5 experiments that you care to mention. It could be 5 patients in a hospital, living or dying. It could be 5 football matches. It could be anything. So if and I want to know the distribution of the number of successes. Zero, 1, 2, 3, 4, or 5. Okay. So for 5 trials, we can have this number of successes. We can have a clean run of successes, all success, or all failures. But for the examples, I will need to know P, which equals the probability of an individual success. An individual success. So in the example of taking 5 football matches, you need to know the probability, let's say the home team wins. And quite often, you'll choose P equals 0.5, 0.5. So the example to have in mind is a coin. So probability equals 0.5 is a nice standard way to start these things, because it's symmetrical between failure and success. You'll observe that if P equals the probability of success, then 1 minus P equals the probability of failure. Okay? Because all the probability that's not in success is in failure. Later on in the course, we'll talk about how to estimate what this probability is, but for the moment, I'm just going to assume it's known and understood. And we've covered this in great detail in 715184. So this is just a very fast revision. Okay. So we've got 5 trials, and I want to work out the distribution of how many successes there are. Just looking at it, it's pretty obvious that you're going to get 2 or 3 successes if P equals 0.5. But we'll work that out more precisely. So let's just say, for example, we have R equals 2 successes. Okay, that's just an example. But we'll notice that we can have, if I say T or F, I say T for true and F for false. That's another dichotomy there between another way of describing Bernoulli variables rather than success or failure. So if I've got 2 successes, that's out of 5, n equals 5 trials. Then we can have T, T, F, 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 or T, F, T, F, F, or F, F, T, T, F. Lots of different ways of organizing those. Organizing those 2 successes in the 5 trials. You can see here that we've got 2 successes right at the beginning. Here there's one there and one there. Here they're over there. And they could be in any place. They could be right at the beginning. I don't care where they are. Which makes sense if these trials are independent. If these trials are independent, then the fact that this one's true can't possibly affect this one. They don't talk to each other. I'll refine this concept later in the course. It's a very tricky, very slippery concept, is independence. It's very easy to abuse it statistically. And that's why I'm being rather circumspect about exactly what it means. But really what it means is that if I cover up one of the results, you can't look at the other ones and see whether it's more likely to be a true or a false. If I put my hand over this one, you don't know. You've got no information about what's in what that one is from the other 4 that you can see. There's no information crossing. They don't talk to each other. There's no information transfer. Okay. So if I work out what the probability of this one occurring is, what's the probability of that one occurring? Well, we've got to look at this one. This one being true, the probability of that one being true is just p. I specified it, I've rubbed it off. Oh, here it is. It's 0.5 in the examples that I'll be covering, but we'll just write it as p for the moment. And I'll be able to substitute 0.5 into it later. That's the first one, times p for the second one, times 1 minus p for the third one, times 1 minus p for the fourth one, times 1 minus p for the fifth one. P, 1 minus p, 1 minus p, 1 minus p. So that's equal, for this top one at least, that's p squared 1 minus p cubed. You with me? You stop me if I'm talking too quickly. You should all know this is all revision, but we'll get rid of that. But you can see that all of these probabilities are the same one. Let's take this one, for example. That's p for the first one, times 1 minus p for the second, 1 minus p for the third, 1 minus p times p, which is again p squared 1 minus p cubed. What I'm doing is working out all the possibilities, all the possible ways of having 2 successes embedded in 5 trials. And of course, because you've got 2 successes, you've got 3 failures, because you've got 5 trials, and that's fixed. We'll see later on in the course what happens if you don't know the total number of trials. But here, let's just say we've always got 5 trials. It might be a football league with exactly 5 matches in it. So the probability of having 2 successes equals some number, which I'm going to call k, and I'll fill that in a minute, times p squared 1 minus p cubed. Because all these lines here and all the other ones that I haven't bothered finishing off have all got the same probability, but I need to multiply it up. I need to multiply this figure up here by the number of different lines that I've got with 2 successes in. Because I don't care where those 2 come, and they could come right at the beginning, right at the end, right in the middle, or scattered through. I don't care. Yes? So we need to work out what this k is here, because k is a particular number, so k is a combinatoric term. Because it's the number of ways of combinations I've got of arranging those. Can anybody remember how to calculate that k? Do you remember what it is from 715? Anybody remember that? I'll write it down. So we've got, what I want is I seek the number of ways of arranging R successes and n minus R failures. So a total of n trials. Okay? So how many lines like this are there? Well, I could just write them out and count them for 5 and 2. But I want a general result for general n. What happens if n is 10, or n is 100, or 1,000? If n is 1,000 and r is 500, there's going to be like a million, billion, trillion, gazillion, billiton, skeleton combinations. So we need a formula. What I'm going to do is, I'm just going to write it out because I'm going to expect you to be familiar with the factorial function. Can you remember the factorial function? Yeah? Equals n factorial. Because it's the number of ways of arranging n objects. Okay, 1, 2, 3, 4, 5 in this case, but the number of ways of arranging them is n factorial. However, what I've got to divide by, in this case, I've got to divide by 2 factorial, because if I just arranged numbers 1 to 5, 1, 2, 3, 4, 5, I could arrange it 1, 4, 3, 2, 5, or 1, 5, 2, 4, 3. I guess I can arrange them in any way of 5 factorial ways. I'm double counting here because if trial 1 and 2 are successes, well, that's the same as writing 2, 1, 3, 4, 5. And that's the same as writing 1, 2, 4, 3, 5. Okay? If I rearrange these terms here, then I don't care that that is the first true that I've had and that's the second. And I don't care what order I see the falses in either. So I've got to divide this n factorial, which is the total number of ways of arranging those rows, by, well, I'll just write it out, divided by r factorial n minus r factorial. Okay, because that's the total number of ways of arranging n trials. But I've got to divide by the fact that I don't care which order these trues come in, because true and true is the same as, I can swap it over, and I can write those in any order as well. And of course that's 3 factorial and that's 2 factorial. So we've got this formula here for the total combinatorial term, which is this term here, this k times that, which is this. Sometimes I'll write that down as nr in brackets like that equals n choose r, which is a nice way of thinking. So I've got this solution here to the combinatorial term. Very quick introduction to it, but this should be familiar to you from last year. Where's my eraser? Okay, so we've got n trials. We've got r successors. The probability of this equals n factorial over r factorial n minus r factorial, p to the r 1 minus p n minus r. Where did I get that from? Shall I go pick this formula apart here? R equals the number of successors. N minus r is the number of failures. And n is the number of trials. I want you all to get into the habit of writing out formulas. You're doing it in this context. You're doing it in the context of being in a lecture and copying what I'm doing. I want you to get into the habit of writing out these formulas when you're thinking about it. Use the writing, use the paper, use the act of writing as a guide to your thinking. Okay. So n factorial over r factorial n minus r factorial is just this term here from the combinatorics. This p is the probability, that's probability of success to the power number of successors. And this term here, which I'll sort of draw here, is the probability of failure to the power number of fails. Okay? And this is known as the binomial distribution. And now we'll use R to verify some of this. Let's see if this works.